So I think you're going to enjoy this much more because I'm going to show you some real solutions. I'm getting to a point where I would like to just see some of the computations drawn out rather than the ones that they have in Zekma and Glow. So I did some of those, and I tried to give you some assignments from the Shams outline that's a little bit more accessible. So the wave equation, I'd like to do a derivation of the wave equation, but not a derivation in the math sense, but a derivation that, you know, kind of an engineering style derivation. So the idea of a vibrating string to me is a guitar string. You're going to pull a guitar string. And the string on a guitar string is actually held at both ends, clamped down. So you can think of the string as having length L and being held down, and that string is vibrating up and down after you pluck the string. So the derivation of the wave equation, or where it comes from, is exactly the same thing that you do for any one of the other equations. You take a little section of the string and then magnify onto that little section. So there's that magnified section blown up, and you start with an arbitrary point on this section. So here's my arbitrary point. So that point, it's vibrating. So I've still framed that string with a little magnified piece, and you picture it vibrating up and down. And you can consider the displacement from ground zero. So it's going up and down above ground zero, and there's this displacement. Whenever it's above, it's going to be a positive displacement, and whenever it's below, it's going to be a negative displacement. So there's some kind of displacement. And it could even be that there's horizontal displacement. That's totally valid. So behind every model, when you're doing models, not a derivation, it's model development, that's what I would call it. There's always a list of assumptions, and you have to list these assumptions down. So the first assumption that we're going to make to derive the wave equation is that there is no horizontal displacement. The only displacement that you're going to see is vertical displacement. The second assumption is that we're going to assume that there's no resistance to bending, which if you have a guitar string, that's not true. Do any of you play guitar? I play guitar, so that's not true. You have some resistance to bending, but we're not going to assume that there's any force pulling, resisting that string being pulled. So the material is perfectly flexible, no resistance to flexing at all. That's assumption 2. So really, the only forces that are pulling on the string are the tugs. In the little magnified section, the only pulling from the string is going to be from these two tugs right here, from the other portions of the string tugging it back down. And that tugging has a name. It's called tension. And again, because it's tugging in this direction, it's going to be tangent to that little piece that I have. So if I let T of xt be the magnitude of the tension force at time point at the location x, so if I made a little number line along my fretboard, the x would represent the magnitude, T of xt would represent the magnitude of the tension pulling that way. So it's the magnitude, it's not the actual vector field, it's the actual magnitude. And then since we have a little piece, the way we do this in calculus is that we say, I've just moved a little bit over to the right, I'm going to call that x plus delta x, and then the tension to the right side would be T of xt plus, or T of x plus delta x, comma t. The obvious candidate for what law you're going to build this equation on is Newton's second law of motion. Force equals mass times acceleration. So that's the groundwork. I was trying to explain this the other day to pharmaceutical companies and the FDA, that it is not a statistical equation. We begin with a law of physics. So there is no, they kept asking me if I'm fitting data. I'm like, no, that's statistics. I already have an equation. I start out with a law, like Newton's second law of motion or the first law of thermodynamics, that already gives me an equation. And that's where we start out. We have an equation, and then we're going to build the model terms for each one of these equations, for the equation based off of the assumptions that we just listed out. So I need some variables to keep track of. U of xt would represent the displacement of the string from the line, from the horizontal line, and I've marked it in red on the picture so you can see it. Acceleration then would be the second derivative of the displacement. So That's what we get for the acceleration. M is the mass of the segment. And mass, we can have another law of physics that says that mass is equal to density times length. That's not nice, because we need arc length to capture the length. It's a curved piece of string, right? So we need the formula for arc length. And if you remember the formula for arc length, it involved integrals with square roots in them. So they're not, it's a very nasty section of Calc 2. Very deceiving, because students think, oh, this nice little formula that's sitting here. But almost anything that you put into the formula will end up being a big mess, other than f of x equals 0 or f of x equals 1. Even f of x equals 1 can give you a run for the money. So assumption number 3 is that we're going to assume that the vibrations are small and that we're not going to have an arc. If the vibrations are small, then that length is going to be, so this length, I want to point to it, but here I'm going to use the mouse. This length right here on the yellow piece is almost close to just that horizontal length here, and then I can get away with the fact that I don't need to use the arc length formula to do an integrals to get any of the length pieces. So that length I know, it's delta x. So far so good? You like my engineering derivations? If I just didn't get fascinated with the tools, I would have made a good engineer. So here we are now. We have these two pieces. I'm going to take that little segmented piece, see where I put a rectangle around it, and blow that up. Okay, so you can look at it. And underneath that blow up, you see that horizontal line I've drawn underneath it? I'm just taking that piece right up here that's in the horizontal box and putting it down there and giving myself a little reference line. So this line has nothing to do with this line. It's actually a line that I drew right here. But I didn't want to mess up the picture anymore, so I drew it right below so you could see it. The tension can be thought of as a resultant vector. Right? So you can think of it as being the resultant vector between two pieces. Well, we know how to find the angle, that angle between, right? There's a formula for it. And if we assume that the magnitude of v is 1, it turns out that that vector v that I've drawn here at the bottom, that vector v that I've drawn here at the bottom, I can actually crank out the magnitude and it becomes t times cosine theta. Good to go? All I'm doing is formulas from Calc 3, formula between angle between two vectors, and I'm making some assumptions about the magnitude of some of those vectors, that they're normalized, and that gives me this formula for the magnitude of v. Well, if that side is t cosine theta, the other side is t sine theta. So I drew the little picture that I've now blown up and tried to explain here. I've drawn it back up here. And then I also have a similar picture down here. But the horizontal components, let me back up 1 second. This horizontal component is pulling in this direction, in a negative direction. Where's my mouse? Right there. And this horizontal component here is pulling in this direction. They're opposites of each other, so they're going to cancel out. So really, the only pieces is the vertical displacement that's important. So only the up and down motion here is what's important. And I know what the formulas of those pieces are. I just cranked that out for you. It's t sine theta, right? So I just replace the t of x. I'm just giving you, that's a magnitude I'm giving you. So far so good? Yes? So the force that's really acting on the string is going to be the right force minus the left force, which I have expressions for. And the theta is a function of where you are on the string. So it's a function of x, and it's also a function of the time the vibration is going on. So theta itself is a function of x and t. So now we have an equation. Force is equal to mass times acceleration. If we divide both sides by delta x, we have this. and take the limit, right? That's the obvious thing. As soon as you see a delta x, you know what's going to happen. At some time or other, since we're math people, we're going to take the limit as delta x goes to 0. So now we have an equation, but it doesn't look like the wave equation yet. The wave equation has no t's in it and thetas in it. So the right side looks like part of the wave equation, but the left side doesn't. So let's reduce the left side a little bit more. Here's the string again, and there's a tangent line to the string. The slope of the tangent line is ux. Agree? The derivative of ux is approximately equal to sine theta. So if I drop that assumption in, instead of sine theta, I'm going to drop in ux. Well, now I have t times ux. If I make one more assumption, or two more really, 2 for 1 here on assumption 4, I assume that t is constant and rho is constant, the density is constant. If I assume t is constant, I'm assuming that it's perfectly elastic, perfect elasticity. And what I get is the familiar look of the wave equation once I make that assumption. Because if t is constant, I can pull it out, and I get the derivative of ux, which is the second derivative of u. So I get utt is a constant times uxx. And that's the wave equation, right up there. The yellow is the wave equation with the constants in it. And if I could scale, if I scale time, or you might see the form of the wave equation where they call c the speed of the wave. You might see it in this form. So this explanation that I just gave you was taken from a website with on YouTube where the guy didn't say his name. It was a guy. But I kind of elaborated a little bit more and organized a little bit more than what he had. But it's coming from somewhere on YouTube where you can watch it yourself. One step back here. The c squared, it's a constant. I can scale that constant out just the same way I scaled the constant out from the heat equation last week. So the form that you usually see in math textbooks is UTT is equal to UXX, or UTT minus UXX is equal to 0, something like that. So you won't see the constant in there at all. Okay, questions?